Welcome everybody, and in this PowerPoint we are going to be analyzing the Earth, Moon, and Sun system. Within our PowerPoint we are going to look at different motions or movements such as rotation and revolution. We're going to explain how the Moon goes through phases and look at how eclipses occur. Some important vocabulary and objectives as well: rotation, revolution, perihelion, aphelion, different types of eclipses, and more. Obviously, the Earth, Moon, and Sun system is important to us on Earth, but we have been studying this for a long time. If you look here and look at Stonehenge, people believe that this was created in a way to study the seasons. At the beginning of the summer in the northern hemisphere, around June 21st, the rising sun would come directly above the heel stone of Stonehenge. So this is not something new. Okay. In addition to this, we have been studying this more recently, and where we will start is the motions of Earth. Right? There are two main motions of Earth that we are going to be looking at. Number one is rotation, which is Earth spinning on its axis at a rate of about 15 degrees per hour, and the second is revolution, all right, or the orbit of Earth around the sun. Right? Now, as we also look at rotation and revolution, we will look at a motion known as precession. Right? Precession is a very, very slight movement over the course of about 26,000 years or so of Earth's axis. So if you guys look, Earth's axis is currently pointed about 23.5 degrees from due center. So we do not orient ourselves straight up and down. We are tilted, and as you can see, we are tilted towards Polaris, or the North Star. This precession is going to be a slight change in that Earth's tilt, and as we said, that occurs very, very slowly, but it happens over time. Starting with rotation, Earth's rotation is a very, very standard motion where Earth is just going to spin on its axis, and that gives us day and night. Right? It takes us about 24 hours to complete one rotation, and we rotate counterclockwise. Right? In addition, we also see some effects from Earth rotating. Some things that we see is the sun traveling across the sky throughout the day. The sun is obviously not moving. It is our rotation which is causing that motion, or that apparent motion. Also, stars at nighttime also appear to move, and once again, that is due to Earth's rotation, not because of those stars actually moving. All right, on to revolution. Revolution is the motion of Earth orbiting around the sun, and this gives us a year. If you guys look, it says that the Earth's average distance from the sun is about 150 million kilometers. However, that is going to vary over time, meaning that there are actually positions within Earth's orbit that is closer to and farther from the sun. Now, this is one of the most common misconceptions in science. Many people believe that when the Earth is closest to the sun at this perihelion position, that is summertime. That is not the case. If you look, Earth's perihelion position, or when we are closest to the sun, is actually in January, right in the middle, or right at the beginning, I should say, of winter. Earth's aphelion position, or when we are farthest from the sun, that is in the northern hemisphere summertime, about July 4th. So distance from the sun has nothing to do with Earth's seasons. Furthermore, because of Earth's annual movement around the sun, each day the sun appears to be displaced among the constellations at a distance of about 1 degree, meaning it takes us about 365 days to orbit around the sun once, and obviously the amount of degrees in that oval shape revolution is 360. So about 1 degree per day is going to be the change. Now, to explain the seasons, as we said, the distance from the sun has nothing to do with it. So what actually causes the seasons? Well, if you notice, the Earth has a tilt of 23.5 degrees. That is very, very important. If you look, Earth's tilt is going to cause the sun's rays to hit the Earth differently throughout the year. So if you look at June 22nd here, the summer solstice, that direct sunlight is hitting the northern hemisphere. Direct sunlight, more intense, warmer weather. If you look at December 22nd, the direct sunlight is hitting the southern hemisphere. So that would be the southern hemisphere summer, and the northern hemisphere is winter. Now, why is it the northern hemisphere is winter? Because once again, we are not getting direct sunlight. We are getting indirect, low-angle sunlight, which does not carry a lot of energy with it hitting the northern hemisphere. It's more bouncing off of the surface. So these are our main 4 seasons throughout the year. We have the winter solstice, which is around December 21st. We have the vernal equinox or the spring equinox, which is about around March 21st, 3 months later. We have the summer solstice, which is around June 21st, once again 3 months later. And then we have the autumnal equinox, which is around September 23rd, once again 3 months later. Those are our 4 main seasons on Earth. Obviously, the equinoxes, meaning kind of intermediate seasons. Equinox in Latin stands for equal night. So those 2 positions, every location on Earth will have 12 hours of daylight and 12 hours of night. So that is where we get the word equinox from. The main 2 are the polar ones where we have the solstice, right? The solstice, winter solstice, once again, that is our winter because we are not receiving direct sunlight. And the summer solstice is going to be our summer because we are receiving more direct light. Once again, this is all because of Earth's tilt. Moving on, we're going to spend a second on this, talking about precession. That is going to be our 3rd motion that we'll talk about, and that is just a slight change in our tilt, meaning as our tilt is now, we are 23.5 degrees pointed towards the North Star. 23.5 the other day would be towards a star known as Vega. A slight change in the tilt would result in the tilt varying a little bit over time. It's very similar to the wobble of a spinning top. So since the Earth is wobbling, or should I say spinning, it's very similar to this motion, right? So this period of precession is about 26,000 years. In the year 14,000, we'll point towards the bright star Vega, which will then become the North Star. And by the year 28,000, North Star Polaris will once again be what we call the North Star. So this kind of changes over time. Right now, our North Star is Polaris. Right? Polaris precision only has a minor effect on the seasons because the angle of the tilt only changes very, very slightly. It does, however, cause the seasons to move slightly within the orbit, so seasons are affected a little bit, but not very much. Okay. The Earth-Sun motion, in addition to its own movements, Earth accompanies the Sun as the entire solar system speeds in the direction of the bright star Vega at 20 kilometers per second. Also, the Sun, like other nearby stars, revolves around the galaxy. Right? So we have a lot of motions going on in this Earth, Sun, and Moon system. Right? Now, going back to the motions of the Earth-Moon system, Earth has one natural satellite, which we call the Moon. Right? So Earth is going to make its trip around the Sun, and our Moon is going to come with us. It's going to orbit the Earth as we do this, taking about a month for the Moon to go around the Earth. Because the Moon's orbit is also elliptical, the distance to Earth varies by about 6%, averaging about 384,000 kilometers. So just like we had aphelion and perihelion, the Earth-Moon system is going to have perigee and apogee. So perigee is when we are closest to the Moon, and apogee is when we are farthest away. Right? The motions of the Earth-Moon system constantly change the relative positions of the Sun, Earth, and Moon. This results in changing appearances of the Moon, which we call moon phases. Right? So different amounts of the Moon are going to be lit up by the Sun. Notice that the Moon does not create its own light. Instead, it is simply reflecting sunlight. Right? So if we look at this diagram, you notice that we have the new Moon at position 1, a crescent at position 2, a waxing crescent, meaning waxing, there is more of the Moon being lit up. At position 3, we have a first quarter. Position 4, we have a waxing gibbous. Once again, waxing gibbous because we have more of the Moon lit up. Gibbous meaning more than half. Then to position 5, we have a full Moon lit up. So we see the complete side of the Moon that is being lit up by the Sun. Now position 6, now we're going to start to see less of the Moon lit up. So we are now waning. So this is a waning gibbous at 6, onto a third quarter at 7, and a waning crescent at 8. If you look at positions 1, 2, 3, 4, 5, 6, 7, and 8, if you look at the Moon on its orbit around the Earth, you will notice that every time the Moon is half lit up by the Sun. the half of the moon that is facing the sun, or the sun's rays, is lit, and the half of the moon facing away from the sun is dark. Right? So half of the moon is always going to be lit up, but it depends how much of this half we actually see and how we name moon phases. For example, number one, notice we see none of the lit part of the moon. We are seeing the full dark side of the moon. We call that a new moon. Looking at position 5, we see the full lit up part of the moon, so we call that a full moon. We see the full lit part of the moon. The half that is lit, we call it a full moon. And everything in between, from waxing crescent, waxing gibbous, to waning gibbous, waning crescent, and your first and third quarters. Alright, so once again, lunar phases are a result of the motion of the moon and the sunlight that is reflected from its surface. Half of the moon is always illuminated to an observer on Earth. You're going to see different percentages of that lit part of the moon depending on the moon's position around the Earth in respect to the sun. Right? The cycle of the moon through its phases requires about 29 and a half days, a time span called the synodic month. This cycle is the basis for the Roman calendar. However, this is the apparent period of the moon's revolution around Earth and not the true period, which takes only about 27.3 days and is known as the sidereal month. Right? Now, 27.3 is the amount of time it takes for the moon to go around the Earth. However, it takes 29.5 days for the moon to show all of its moon phases. Right, lastly, that's going to bring us to eclipses. Now, sometimes when the Earth, Moon, and Sun line up completely, you are going to get an eclipse. An eclipse is when you cannot see either the Moon or the Sun because of the specific positions of the Earth, Moon, and Sun within the system. Now, always remember, an eclipse is named after what you cannot see. For example, a solar eclipse is when you cannot see the sun. That is when the moon gets right in position between the Earth and the sun, and it blocks out the sun for a small location on Earth. Now notice, you do not always have a solar eclipse once a month because the moon's orbit is inclined about 5 degrees to the plane that contains the Earth and the sun. So what does that mean? That simply means that the Earth, Moon, and Sun system is not going to line up every single month. It is a much more rare event because of that slight incline on the plane. Right? Now, a lunar eclipse is going to be when the Earth's shadow blocks out the moon. Right? So we have a full moon, the sun's rays are hitting the earth, just like you cast a shadow on the ground, the earth casts a shadow into space, and when the moon enters that shadow, that is going to cause a lunar eclipse. The full moon is blocked out from entering Earth's shadow. Right? Some information about eclipses. Definitely make yourself aware to. So that is all for this PowerPoint presentation. What I would recommend is going through, reading everything a little slower and in a little more detail, and asking a question if you have any. Thank you for listening.